Good morning. We continue with our lecture on heat treatment of steel. This is the fourth lecture on this topic, and if we recollect what we covered so far is we looked at transformation diagrams, phase diagram, because they help you in understanding the basics of heat treatment. We talked about the different types of transformation that takes place: paralytic, martensitic, benetic transformation. We looked at isothermal kinetics. We looked at today we will look at the process of austenitization. We will look at effect of alloy element on the TTT and phase diagram, and we also have looked at already the CCT diagram. And last class we introduced three common heat treatment processes: annealing, normalizing, hardening. And today we will concentrate on this, and last class we discussed this primarily with respect to eutectoid steel. Today we shall look at how this process changes with if the composition or carbon content in steel changes. And if we look at these three heat treatment processes for eutectoid steel, what we do is we take the piece of steel, heat it to a temperature. So, this is the heating cycle, this is the soaking cycle. You have to soak it for certain length of time, so that the temperature from the surface to the center of the job becomes uniform, and this whole time will depend on the size or dimension of the job. And then if you are hardening, what you do, you have to quench in a liquid, and one of the ideal or very good quenching medium is water. So, you quench in water, and if you are normalizing, take out the sample from the furnace and let it cool in air, still air. So, air cooling, this process is known as normalizing, and I am representing it as by N. And annealing, what you do, you just after soaking you switch off the furnace. So, in that case the cooling is called furnace cooling, and you allow, that means the cooling rate is extremely slow. If you superimpose these cooling rates on the time temperature diagram, then you will be able to follow the nature of the transformation that you expect. Now, this is when if you are doing annealing, where the cooling rate is nearly equilibrium cooling rate, is a slow cooling rate, and this is the type of plot that you may get if you plot temperature against log time, and this is furnace cooling. So, this is annealing. If you cool in air, then it is air cooled, this is normalizing. If you water quench, the quenching rate or cooling rate is very fast, water quench, and here you get a totally a different kind of structure. Now, what type of structure will you get here? So, consider this particular case, annealing, and once during annealing, this is the CCT diagram. On the CCT diagram, this shows the time as it crosses this, then the decomposition of austenite starts. It is an eutectoid decomposition. Austenite, which is face centered cubic, which has a face centered cubic structure, it transforms into a mixture of ferrite and carbide, which is called cementite. This has body centered cubic structure, and when this happens, you have a nucleus of cementite nucleating or forming at these interfaces, and when this forms, the surrounding region, when this cementite forms, surrounding region gets depleted of carbon content. Therefore, simultaneously you have a ferrite plate or a region, a ferrite grain will nucleate just beside cementite, and this process goes on, and this is called perlite, and this grows in all direction until and unless it meets another such perlitic region. In that case, there is an impingement, and ultimately each of these grains, austenite grain, will be converted into several numbers of perlite nodules, and what you have finally, the structure will consist of perlite, which is which has a lamellar structure, which is made up of alternate layer of ferrite and cementite. Now, here since the cooling rate is very slow, it cuts or intersects the CCT diagram near the top half of this. So, therefore, the lamellar spacings between two consecutive cementite plate, this is cementite, and in between you have ferrite. So, this distance is the interlamellar spacing, and this distance is large. So, in annealing structure you have a rather coarse structure, and this can be easily resolved under optical microscope. Now, the process of transformation in case of air cooling also will be exactly similar, only difference will be the rate of transformation will be faster. So, when this cementite grows, the rate is so faster. So, that means the nucleation of both cementite as well as cementite as well as ferrite plates, they form one after the other, and the process is so fast. So, in this case the lamellar spacing will be smaller. So, it will be more difficult to resolve. So, this here you will have fine perlite. So, this has lower or smaller lamellar spacing. Whereas, in the other case where you are quenching, in this case you do not allow any movement of carbon atom. When perlite in cementite nucleates here in austenite, carbon atom has to move over a relatively long distance, and in this case when you are water quenching you do not allow such movement. So, the transformation takes place through a diffusionless transformation process, which is athermal. We looked at it characteristic, and in case of an eutectoid steel the carbon content is quite high, 0.8% carbon. So, here what you expect is a plate type of these cementite the martensite plates will form, and these plates will be made up of very micro twins, which will be not possible to detect or see under optical microscope. Even and these plates when they grow, they cannot cross this boundary. If it starts from here, it will end in the boundary. If it starts from here, it will end on the boundary, and later on subsequently when this new needles form, they form like this. So, in this way here the structure will be made up of martensite, and this martensite process is a diffusionless process, and it takes place through shear mechanism. There is deformation in the lattice, and which increases which makes this steel very hard, and also since carbon atom is kept by force in solution, this also gives substantial amount of solid solution strengthening. Now, whenever these needles develop, this any decomposition process, whether it is austenite to ferrite plus cementite, or whether it is austenite to martensite, you look at this has a this side you have a closed pack structure, and when this product forms you have this is BCC, it is rather open, this is BCC. So, there will be substantial volume expansion, and that is why surrounding regions there will be a lot of the stress fields develop, and sometime it can prevent a part of this between these plates you may have some amount of retained austenite left. So, when you quench ideally at room temperature, although you expect full martensite, but because of this constraint when it expands and the process is very fast, what happens, the surrounding region, this untransformed region, there will be such a high level of stress which will not allow compressive stress, which will not allow the austenite to transform, because for austenite to transform it needs space to expand. So, if that space is not provided, in that case some amount of retained austenite will be left behind. So, your microstructure will be primarily martensite and maybe some amount of retained austenite. Structure will be so fine that it may not be resolvable, and in fact, under optical microscope these martensites also these are very bright, and they often do not etch well although these boundaries, but if you temper it slightly, as we will see, they etch very well and you can see this structure even under optical microscope, but not the final details within one plate of martensite, because there the level of resolution needed is in the nanometer region, I mean that is extremely small. So, you need electron microscope to resolve the structure within the plates, martensite plates. Now, here if you look at that hardness, as you increase the cooling rate, hardness goes on increasing, and so this is the Rockwell hardness of after hardening. This is in a normalized, this is in case of annealing. So, this will be the sequence. Now, let us see let us look at what will be a comparison between these three processes which are listed here. In annealing you get coarse pearlite, in normalizing you get fine pearlite, hardening you get martensite, but in some cases it is mostly, I mean it is expected to be single phase, but sometime because of that volume expansion some amount of retained austenite may also be there. Now, the section size effect here, since you are cooling at a very slow rate, the temperature gradient between this, if you have a job will always have a dimension, though therefore, if you are cooling at a very slow rate, the temperature difference between the center and the surface will be very little. So, here we do not expect much of a section size effect. In a normalizing, you are cooling it in, it is air cooled relatively fast. So, there may be little more difference in cooling. So, here you may see, depending on the job that you job size, you may have some amount of some little effect, section size effect, but in the case of a hardening where you are quenching, there will be a large difference in temperature between surface and the center. So, therefore, this will have a good section size effect. The hardnesses which are mentioned, they are rough guidelines, and another reason is residual stress, since here the gradient, thermal gradient is very low. So, therefore, you do not get any residual stress here, but in normalizing depending on the section size. So, normally it is low, but if the job is large, then there is a possibility there may be some amount, whereas hardening you may have land up with very high residual stresses. About stability, the anneal structure, this is more stable. This will be also is a stable structure, but may not be, since the lamellar, I mean it may not be as stable as this, and this certainly the structure is unstable. You also have untransformed retained austenite. So, therefore, this structure is unstable and it can transform even at a room temperature or long holding, or subsequently if the temperature goes up a little, that there will be structural change here. Ductility in this case will be very good, it will be medium good, and here this will have a very poor ductility. In fact, this high carbon martensite is very brittle. Look at this now having done that, let us now look at the heat treatment of hypoeutectoid steel. Now, hypoeutectoid steel, if you know, that means carbon content is less than the eutectoid composition, which is around 0.8% carbon. And the typical the satiety diagram, if you recollect, there will be an additional line here which will represent start of precipitation of proeutectoid ferrite. So, this part, this is the A1 temperature, lower critical temperature, this is the upper critical temperature. So, this phase diagram this continuous cooling diagram, CCT diagram for hypoeutectoid steel, which will help you in understanding this process that which is drawn over here. And here also, if you cool very slowly, you get, this is furnace cooling. So, this is annealing, air cooling, this is normalizing, and you quench in water, then it is hardening. Now, this structure is actually will be very similar to what we talked about. There may be a little difference over in these two cases in the microstructure. So, here what will happen, once it crosses during annealing, you will have proeutectoid ferrite grains forming, and this will be most likely place will be these grain boundaries, grain corners. So, these grains will form, and this process will continue until it reaches this point. Once it reaches this point, at that time, and remind you, when this process of precipitation of ferrite continues, the composition of austenite will keep changing, and when it reaches this point, say goes below this eutectoid temperature, the composition of austenite around this will be close to 0.8% carbon. And this is when what happens, the perlite nucleation starts, and perlite nucleation here also can take place from here, and you will have these perlite nodules forming. This is how. So, what we will have? You will have proeutectoid ferrite plus coarse perlite in case of annealing, and this amount of, since it is a slow cooling, amount of proeutectoid ferrite will approach the equilibrium value, equilibrium amount as predicted by the phase diagram. Whereas, in this case also the structure will consist of proeutectoid ferrite. Some of these ferrites can also form as an Widmanstätten structure, say some ferrite plates forming here, and then balance will be converted into perlite, and this perlite which forms here, look at it here, the precipitation of proeutected ferrite takes place at a much lower temperature here, and annealing it starts from here, here it starts from around here. So, therefore, you have a higher driving force. So, you may have this kind of an Widmanstätten ferrite also forming, because the process is quite fast, and balance you will have remaining will be perlite. and this perlite will be fine. So, you will have proeutectoid ferrite plus fine perlite, and here I think I will go into this, it will be martensite plus, depending on the carbon content or composition, there may be some amount of this is martensite and plus some amount of retained austenite. Now, the question comes is I think now, in the case of hypoeutectoid steel, just we looked at all annealing for hypo, we have seen this side of the composition irrespective of whether it is annealing, normalizing or hardening, you heat it in this temperature range. Whereas, in case of a hypereutectoid steel, there is a little difference, and what is this difference? In case of a normalizing, you can heat it above this line called ACM line, where this line represents the temperature at which proeutectoid cementite starts precipitating. Whereas, for annealing and hardening, your austenization temperature is in this region. Now, obvious question comes why. So, in case of here also, when this when you form austenite, so you will have, say in case of a normalized structure, if you are heating here, you will have austenite, completely austenitic structure is fully austenite, and then you are cooling by you follow air cooling, and what happens as the temperature goes below this. So, that means on the CCT diagram, you have to look at that CCT diagram rather. So, this is an isothermal diagram, CCT diagram, possibly this benitic region may not be there in plain carbon steel. So, you have to look at this part, and when you are cooling, so proeutectoid cementite precipitation starts from here. So, here you have austenite and here you have austenite plus cementite, and this proeutectoid cementite will also form at the grain boundaries. Initially they will form at the grain boundary, and usually the composition amount of cementite that will precipitate out may not be enough, because this process cooling rate is higher. So, this may not be able to form a full network, and before this full network, much before the network can develop, the process of decomposition of austenite to perlite begins, and you will have perlitic structure here. So, you will have fine perlite. Once you cool, you will have fine perlite and broken this proeutectoid cementite, but the network will be broken. Now, you do not want, a main aim is to suppress cementite network formation, because cementite network, it develops along the austenite boundary. This makes the steel brittle and unusable. So, therefore, for normalizing you heat it here just around 30 to 40 degree centigrade above this you can heat. However, for annealing and hardening, if you follow the same thing here, so we will concentrate on this CCT diagram. So, this portion we ignore, which you may not get in continuous cooling. So, here what happens, if you heat it over here, and when you do furnace cooling, you are cooling like this. So, then what happens, here you are cooling it here in this furnace cooling, you are cooling it very slowly. So, that cementite amount of cementite, nearly equilibrium amount of cementite will try to form. So, what happens? You may get a continuous network of cementite. So, therefore, what is done, instead of heating going over there, normal annealing process, you heat it at 30 to 40 degree centigrade above A1, then furnace cool. So, here you have austenite and you will have, these are the carbides. So, normally if you etch with nitel, they may not appear dark, although I am representing it as a dark here. So, these are, and these carbides will not let that austenite grain to grow. So, you will have fine austenite grain, and when you cool in furnace, the balance will be converted into coarse pearlite. So, this is the type of structure you will have. You will have globules of cementite globules plus fine pearlite, and which is a preferred structure. Second is, if you water quench also, from this there is advantages, these cementite carbides, that cementite globules will not allow this austenite to become coarse, and the balance will convert into martensite, plate martensite. This will form into plate martensite. Now, here additionally, if you have cementite particle, it will give wear resistance. So, therefore, if you, the choice of austenization temperature for hypereutectoid steel, we see that annealing, the preferred structure is a globular cementite in pearlitic matrix, and if heated above this, it is likely to develop a brittle cementite network, which is undesirable. So, therefore, you prefer that heating above A1 plus around 30 degree centigrade. Hardening also, you do not get much advantage if you keep more than 0.6% carbon in solution. So, therefore, and when you go above A1, you already have 0.8% carbon in austenite. So, if you quench and this austenite gets converted into martensite, you will get maximum possible hardness, and these cementite globules which remain will give additional wear resistant property. Now, if you heat this case above ACM, the amount of carbon content in austenite becomes quite high, and we know that martensite temperature, MS temperature at which martensite forms, that is a function of carbon content, and it may go, it becomes so low that even at room temperature, that martensite transformation will not be complete, you will have a very high amount of retained austenite. And also that size effect is also important. If the dimension is large somewhere in the core, you may have likely to, you might develop a brittle cementite network at austenite boundary. Now, if you look at a quick look over here. So, we mentioned that when you actually heat steel, you know, if there is a transformation taking place, and this transformation is, you know, when you heat, you have ferrite plus cementite structure, it becomes austenite. So, this will take place. When this takes place, there should be contraction. That means, volume decreases, because this is a closed pack structure. This is a closed pack structure, which is FCC, this is BCC. So, there is a volume, there is contraction. So, when you keep heating, when this transformation takes place, suddenly that steel piece, the dimension will try to shorten, and when you heat, there is accompanying thermal expansion also. So, a very simple experiment one can set up by heating a piano wire, which is shown over here. So, these are some copper connectors. Here you can tie a piano wire here and try to heat this from a power source, maybe a power source like that you use for welding. It is a low voltage high current source, and if you allow the current to pass through the piano wire, this is a bulky, and you may water cool this also, that contact resistance is low. So, this is the portion, if you apply a high current, they will get heated very fast. So, when you heat this wire, what happens, as soon as this critical temperature is crossed, because this process is so fast that when this critical temperature is crossed, you just stop the switch of the power supply, and when it gets red hot, that is the time it gets converted into austenite. So, now what is happening is, during the process there is a thermal expansion, also simultaneously there is a contraction because of this process, and both they balance each other. So, when it becomes red hot, you may still see, it has become red hot, it will still be straight. So, you heat it, and after that if you cool, what will happen? If you cool, suddenly it starts cooling, means it will become from red hot, it will become dull, and which is shown over here. That is primarily because transformation does not take place immediately. Look at that transformation diagram. The piano wire will be close to an eutectoid steel, let us say, and you have this. So, when you are cooling in air, you will pass through, say, let us say this region. So, transformation, when see here it is red hot, when it cools down it becomes dull. So, here that glow is not there, and once this transformation starts, this transformation austenite to alpha plus, this is a phase transformation taking place. Here there is this is an exothermic reaction. So, heat comes out, this is exothermic. So, therefore, it again get heated up, and you may question that will it exceed again this, that does not happen, but it may temperature while it is. So, that means, when the temperature is going down, suddenly it gets heated up and again cooled. Your eutectoid temperature is possibly here, and this rise is large enough to make it red again, and that is what you will see. And when it becomes red, you will find that it sags, and this is the case, is there is a thermal expansion, and also there is expansion when this transformation takes place. This also there is a volume expansion. So, both add together, and this sagging here is visible, and after, so this process, this is called recalescence, again getting heated up, this process is known as recalescence, and this experiment it becomes visible, and if you have some temperature measuring device, you can possibly find out the transformation temperature as well. So, therefore, this I have already explained, that during heating wire expands, but when it gets converted into austenite, this contracts, there is no sagging, whereas in the other case both add up and there is a sagging. Now, because of this process of because of this process of volume change and both superimposed with the temperature difference, often when you give a heat treatment, say particularly when you are quenching a job, if you are quenching a particular job, when you quench this portion, quench in water, this cools very fast, fast cooling here, but inside still remains hot. This temperature possibly will come to the water temperature, maybe the room temperature 25 degrees centigrade, but still this still remains hot, maybe close to depending on the carbon content 850 degrees centigrade. So, there will be a large temperature gradient setup, and this gradient setup can lead to thermal and thermal stresses, no doubt, and which is shown over here. So, this is the job. When you quench, the inside is still hot, but outside it has become cool, and because of this large thermal gradient which is shown over here, this is a CCT diagram. On this, the cooling curve for the core and the surface, which is plotted here. Surface cools faster, core cools slower, and both cases we are assuming that cooling rate is fast enough to avoid that nose of the CCT diagram. So, therefore, you are going to have martensite at the both at surface as well as center. But look at when does martensite transformation starts at surface? After this time t, when it crosses MS temperature, and the process is athermal, it continues to take place as long as the temperature goes on decreasing, and it completes over here, and possibly at that time transformation may not have started at the core. So, there is a lag of there is a time lag in transformation that takes place at the surface and the center, and this induces, and this transformation will be accompanied by volume expansion. Imagine qualitatively, if we say that the surface already transformation has taken place, and when it forms martensite, it tries to expand, whereas the center is not allowing it to expand. So, you will have one kind of stress setup, whereas when the transformation starts taking place at the core, which will try to expand, but the surface will not allow it to expand. So, finally, when it cools down to room temperature, you will find that such as a result of this quenching, you will have a significant amount of residual stresses develop on the job, and particularly the nature of the stress will be tensile at the surface, compressive at the core. And this slide explains that origin of these stresses during quenching. This is E is the Young's modulus, alpha is the coefficient of thermal expansion, and delta T is the temperature difference between surface and core. Now, this temperature difference, so like this. So, as it cools down, there will be the thermal stresses will also go on changing, but the material strength also, say at higher temperature material strength is low. As you cool down, the materials become cooler, its strength also increases, its yield strength also increases, which is shown over here. The strength of the material as it cools down with a time, initially when it is very hot, the yield strength is low, whether in tension or compression, this is low, and as it cools down, its strength increases, and whenever this stress develops, whenever it goes exceeds this yield stress, then there is a local deformations, and this is a permanent deformation, and these local deformations can lead to distortion. Now, what we have shown in this particular case is the effect of transformation stresses. you can similarly find out the stresses originating because of thermal stress, but whatever we have shown is this diagram how the stresses developed at various stages of cooling. And once it is finally you come to the room temperature over here, you may find, so which is this time very long time, and here what you will have, you will ultimately find that the surface there is a tensile stress, this side is positive, this is compressive, this is tensile. So, a surface you have tensile stress, center you have compressive stress, and then transformation stress. In this particular case, if you look at the volume expansion, is contribution is possibly much more. So, there is around 4% volume expansion, and this expansion will also depend on the amount of carbon contained, and then 4% volume expansion is much more than that thermal coefficient of expansion. So, therefore, what we can say, during quenching, this stress that develops in the material will be primarily because of this transformation stress. And since in a quench structure you have a high amount of stresses that develop in the material, it is prone to susceptible to cracking, and also we have seen that because of the stresses, the micro stresses which are generated when martensite plates are forming, surrounding region we also have substantial amount of micro stresses. And to relieve these stresses, to remove retained austenite, you need to give a subsequent heat treatment process called tempering. So, since you have this that means apart from residual stress, hardened steel also is metastable. Martensite structure is not the stable structure, it is a supersaturated solid solution of carbon in ferrite, and it also has some amount of untransformed austenite. And if this austenite transforms later, it may lead to cracking, and also if austenite transforms, there will be accompanying volume change, it can lead to distortion. So, it leads to dimensional instability, and tempering is done to overcome this problem. And while tempering, you can heat, this is the hardening step, heating, choking, quenching, and then a heating to a temperature much lower than the critical temperature. You can heat almost up to 700, and depending on the temperature you get that specific properties. And after tempering, does not matter, you can often quench because your productivity, you want a higher productivity, you can quench in oil or water, or you can let it cool in air. Now, then the process of tempering, since you the martensite is unstable, during the process of martensite there will be some phase transformation taking place in martensite, and as a result its hardness will keep decreasing. And you can monitor the kinetics of this tempering process by measuring hardness. And what you can do, you can heat a series of sample, say at temperature T1, temper at a temperature T1, and after tempering for certain length of time you quench to room temperature, measure the hardness and make a plot. So, this gives the kinetics of hardness change at temperature T1, and you will find if you increase the temperature, rate of that hardness decrease becomes faster. And it has also been found that this kinetics of transformation is a function of both time as well as temperature. If you go back the previous, see, look at for a particular time of tempering, you see if you heat it, tempering temperature is higher, transformation is faster. Within that time the temperature drops up to the Rockwell hardness drops up to this level, whereas if you had tempered here it would have dropped only to this level. So, that means this Rockwell hardness is a function of both the tempering temperature and time, and it was reported first by Holloman and Jaffe that if you represent this hardness plot, against a time temperature parameter called tempering parameter, also sometimes referred to as Holloman-Jaffe parameter, and this is temperature in degree absolute, C is a constant, and log time, and this time you can take in second, let us say, and he used it for different certain varieties of steel he looked at, he found the C to be around 14. And what you do, so main advantage is, say if you do the experiment at temperature T1 for different length of time, and for each you have a reported hardness. Similarly, at T2 temperature also you heat it for different length of time, and for each of these combination you will have a hardness. So, you plot this hardness on this y axis, and on x axis you find out the tempering parameter with a combination of this and this, then you say plot it here. Next you find out combination this and this, you plot it here, and you will find that irrespective of the temperature and time, they may fall on a one single master plot. So, this is called a master tempering graph, and which helps you in determining actual tempering temperature in selection of tempering temperature, combination of temperature and time for a particular application. Now, the question comes, what are the structural changes that take place during tempering, which is listed here. If you follow this hardness against that the time temperature parameter hardness plot, you can possibly divide into three regions. Initial region where there is a little change in hardness, second region where is a substantial change in hardness, and a third region where also there is a substantial change in hardness. Now, stage 1, what happens is a high carbon martensite will break down into low carbon martensite and a special form of carbide. It is a metastable carbide called epsilon carbide. This has little higher amount of carbon content than cementite, and this low carbon high carbon martensite has a plate type of structure. So, that is unstable, and low carbon martensites usually have a lath type of structure. We talked about it, and so this is the main change that takes place during stage 1. Stage 2, the main change is if there is a retained austenite, it breaks down into ferrite and carbide, possibly depending on the temperature. If the temperature is high, tempering temperature will be ferrite plus cementite. If the temperature is in the lower that bainite temperature range, in that case it could also be ferrite plus epsilon carbide. And in the third stage, a new that cementite appears. Now, cementite appears, this can happen in two ways. This can dissolve epsilon carbide and new carbide may precipitate, or the carbon concentration gets adjusted and it changes over to cementite. So, finally, and over here you have cement a ferrite plus carbide structure, and this carbide is cementite. And if you continue to temper further, this cementite will grow and it can become very large at a higher temperature, which can be very easily seen under optical microscope. And the main change that takes place whenever this transformation takes place is, one is the type of martensite, and martensites that crystal structure is also a function of carbon content, and high carbon martensite that it has a body centered tetragonal structure, where if you measure by X-ray diffraction or a XRD pattern, you can find out the crystal structure, find out the C axis and A axis, and the ratio of C to A is an indicator of the amount of carbon the martensite has in solution. And if you plot this against, say, let us say tempering time at a particular temperature, you will find that the C by A ratio changes like this. So, therefore, this X-ray diffraction is a powerful technique to follow the kinetics of transformation that takes place during tempering in steel. Okay. And apart from this, we obviously use microstructure also as a tool, microstructural examination to follow the tempering kinetics. And extra diffraction, in this particular case, if you are on the third stage, if you have look at that extra diffraction pattern, you will see apart from the diffraction line coming from ferrite, you may get the diffraction line coming from cementite, which are characteristic of cementite. Whereas, here this stage, if you are taking this diffraction pattern here, if there is sufficient amount of retained austenite, you will also see the peak corresponding to austenite, and you can measure the intensity of austenite peak and compare it with this ferrite peak, and this ratio will give you the relative proportion of retained austenite and ferrite. So, extra diffraction no doubt is a very powerful tool to follow transformation kinetics in tempering. To sum up, the structural changes that take place during tempering, which is listed as a temperature range. In the lower temperature range, you have low carbon, high carbon martensite gets converted into low carbon martensite plus epsilon carbide. Property wise, there is a slight, maybe sometimes slight increase in hardness. Sometimes people reported, particularly in alloy steel, some amount of brittleness as well. Next is, this is the temperature range, where this also temperature range also coincides with the bainite transformation range, and here you will have retained austenite converted decomposes, and the hardness also keeps changing, and parallelly this martensite also will keep changing, and there will be significant change in or drop in hardness. And in this temperature range, epsilon carbide can pick up carbon to form cementite, but these are not resolved in optical microscope. This structure, but there will be marked decrease in hardness. Whereas, above this temperature, this cementite coarsen, and this is the time this clearly the structure will be visible, resolvable under optical microscope. So, this is the fully softened structure, and extent of softening will depend on the maximum as you approach the eutectoid temperature. And tempered martensite, having this hardness around this, has excellent combination of strength and toughness. But then why, what is the problem of this? I think this I will stop here today to overcome. So, what we have considered is today we looked at quickly we looked at primarily these annealing, normalizing and hardening process. We looked at origin of stresses that develop, and how do you remove these stresses, and how do you give the more structural stability to unstable structure that you get in hardening, that is the process of tempering in little detail. And we also looked at the type of structures that develop during annealing, normalizing and hardening in 3 different grades of steel, that is eutectoid, hypoeutectoid and hypereutectoid steel, and we tried to also give the justification on the selection of austenization temperature in each of these cases. I thought of talking about the austenization process, but maybe I will this I have missed today. So, I will go back do this in the next class, and also we will see that there are certain types of transformation processes where there is a possibility you can cut down or the tempering process becomes redundant, because we have seen you can get a widely differing microstructure in steel both by continuous cooling as well as by isothermal transformations. So, there are certain special heat treatments which one can think about, and also there is also a considerable importance on section size. That means, say in case of a plain carbon steel, what is the dimension up to which you can get a quench a martensitic structure? Is it dependent on can you do it in a say if you have a 0.5% carbon in a steel, can you develop fully martensitic structure right up to the center if you quench in water, if the job is little big, say maybe 1 inch diameter or half inch diameter, and where you have more chance of getting completely martensitic structure from surface to the center. So, today I think I will stop here, and rest I will take up in the next class. Thank you.